In Module 8, we're going to see the second order reliability method, or SORM. So, a quick recap, X is our vector of random variable involved either in the resistance or solicitation model. F of X is their joint probability density as represented here or here by the contour. G of X is our limit state function. It's going to be positive in the survival domain, negative in the failure domain. And G of X equals 0 is our limit state surface, represented either here or here by the magenta line. Omega is our failure domain, so all the instances of X, such as our limit state function, is negative. So again, the problem we're trying to solve here, when we have a large number of random variables involved, we cannot visually see what's going on, we cannot plot anything, and we cannot integrate analytically to obtain our exact result. So we need to resort to approximate analytical methods such as FOSM, FORM, or in this case, SORM. And we want to see how can we approximate our limited function, not anymore by a first order Taylor series approximation, a linear function, but in this case, a parabolic function, a function of x squared. So SORM, its second order reliability method, is going to include the second order curvature of our limit state function in order to increase or the quality of the approximation, so decrease the approximation error in computing or beta or failure probability. So the first problem we need to address is how do we estimate the probability content defined by the half space, defined not anymore by a plane, but in this case by a parabola. So this is the essence of SORM. The second one is how do we approximate or limit state function by a parabola in the standardized normal space. So how can we approximate? So once we have defined that parabola, how do we compute the probability? And in the first place, how do we approximate g of x by parabola, or in this case, g of u, because we're going to do this in the standard normal space. How do we approximate that g of u by a parabola? So this is module 8. We're here in the last analytical method in order to evaluate our probability of failure, the second order reliability method. And what you're going to see is that this borrows several of the concepts we've already seen in the FORM method that we've covered in module 6. So beyond the introduction that we've just seen, we're going to look at how can we define the probability content defined in the standard normal space, defined by the half space that is bounded by a parabola. So we're going to see this with a review of the standard normal space. Then we're going to see what are each of the steps involved in the SORM method. And we're going to look at two examples. A first one in 2-dimension, a second one in 3-dimension, where we can see the full the complexity, or at least the full sequence of steps we need to do to apply the FORM methods. And finally, we're going to go through some summary of what we've seen, along with what are the limitations that are still associated with methods such as SORM. So first, let's do a review of the, again, standard normal space. As usual in reliability, all of our calculations are going to be there. So a quick review of that standard normal space. Then we're going to redefine how can we compute in the standard normal space the probability content that is bounded by a plan. So half space bounded by a plan. And then we're going to extend this to the probability content bounded by a half space that is defined not anymore by a plan, but in this case, a parabola. This is going to be what we're going to use for SORM. So we said X was our vector of random variable in the original space. Now U is our vector of random variable in the standard normal space. So U is normal, which means 0, and variance 1, we have all independent dimensions. So the contour of that joint PDF are in 2-dimensional circular, in multi-dimensional are going to be spherical or hyperspherical. And the probability content decrease exponentially with increase in the distance from the origin in any direction. So this is a same property that we're using since module 5, if I'm not mistaken, in order to simplify the calculation. And why can we simplify the calculation? Because if we go in that standard normal space where everything is independent, we can reduce this multi-dimensional integration to compute the probability content in the domain X, such as my limit state function is negative, so my failure domain, over all my joint probability density, I can reduce that multi-dimensional integral by a simply one-dimensional integral, which is defined simply by the distance between the origin and the plane I want to compute the probability into. So I want to compute this probability in that pink zone, my failure domain. And the only thing I need to do if I'm in a standard normal space is what is the distance between the origin and that line. So if I know that distance, which is our reliability index beta, I can directly compute the probability of failure, the probability defined over that domain in pink, by evaluating the CDF of minus beta minus my reliability index. So this is very convenient. This is practical. We can compute uh, with minimal effort what is going to be our probability of failure if we can go in that domain. But this is for the case where we approximate g of u and g of u equals 0 by a linear function. But in the case of SORM, we want to replace this linear approximation by a parabola. So we need, before defining this parabola itself, look at how can we in the first place compute what's going to be the probability content defined by such a parabola in the standard normal space. Because now we want to have a limit state surface and a limit state function, which is going to be a function of u square, so a parabola, and we want to define what's going to be the probability content here. And this we can express in this form. So the probability of failure estimated with form is going to be the probability that beta minus un. So you see that in this case, we're going to reorient our probability content with respect to one of the dimensions. By convention, in the case of SORM, we're going to reorient our vector alpha with respect to the last dimension of our problem, in this case, u2. So beta minus, in this case, u2 or un, the last dimension, plus 1/2 summation of kappa I ui square. So these are my parabolic term, and kappa I are my principal curvature. So the curvature of my limit state function with respect to each dimension. So the probability that this reoriented distance from the origin, so this is going to be taking into account the distance of that parabola from the origin, and the second term is going to take into account the curvature of that parabola. So the probability of this lesser than or equal to 0, that's going to quantify my SORM probability of failure. If we want to be exact, we need to solve this equation if we want to evaluate this probability of failure. But luckily, we have a very accurate approximation given by this simple form that we can use, and that for practical purpose is very close to the correct formulation, where this approximate formulation involved the CDF of minus beta, the same quantity we were using form, times the product of 1 divided by the square root of 1 plus psi of minus beta. So we already have beta from the form analysis. We only need to obtain psi, which is a ratio of PDF and CDF, and kappa I, which are the principal curvature with respect to each dimension. Whereas, as I said, psi is the ratio of the PDF, the standard normal PDF of beta, divided by the standard normal CDF of minus beta, and kappa I correspond to the principal curvature of my limit state function with respect to each dimension. We're going to see in the SORM method how can we compute those principal curvature. Okay, but for now, we just want to see that if we have those principal curvature, if we have the beta from a form analysis, we can directly, easily evaluate the probability content in that region from these information. So the main step we're going to see now is how can we compute those principal curvature kappa I? So in the SORM method, we're going to cover the introduction. What is the basic principle of SORM? How can we make a second order approximation? So up to now, we have always done first order Taylor series expansion of our g of x. Now we're going to see how can we increase that to go to the second order. Then we're going to see that SORM involves some referential rotation. So how can we perform those rotation of our U standard normal space? We're looking at an example of such a rotation, and we're going to see what are the property of that new referential. Then we're going to see if we want to evaluate SORM, we need to do a second transformation. That transformation is not uniquely a rotation, it's going to be a eigenvalue decomposition. So we're going to see how can we extract the principal curvature using that eigenvalue decomposition. And then we're going to break down the complete SORM method in a list of steps. And we're going to finally cover what are the limitations associated with this method. So for the second order reliability method, what we're going to do is that we're going to approximate G of U, that limit state surface defined in the standard normal space, by a parabola. Okay, where the apex of this parabola is going to be centered on our design point U star. So what are the main steps? First, we're going to transform or our problem from the original space X to the standard normal space. Exactly the same step that we've done in the past with form that we've covered in module 6. Then, just like we did for form, we're going to find a design point. So we're going to find a U star in the standard normal space using, again, a form analysis and the IHLRF algorithm to find the most probable failure point. Once we have this, we're going to find simply the principal curvature, because once we have beta, so beta is going to already be obtained from the form analysis. So once we're going to have beta, the only thing we need to extend it to make a SORM analysis is what are the curvature with respect to this dimension. So once we have beta and the curvature, we have everything we need to evaluate that failure probability with SORM. So the first step to find those curvature is to express what is going to be our linearized or parabola-like limit state function. So by a second order Taylor series expansion. So to do this, so far in module 5 and module 6, we've keep seeing this formulation. That was our first order Taylor series approximation of G of U. So remember, we have a term here, which is the constant term, plus the gradient times U minus U star. And since we're finding or we're approximating that first order Taylor series approximation on the design point, by definition, the limit state function of the design point should be equal to 0. Then we only have that gradient times U minus U star. And we now add, if we want to use SORM, this higher order terms. So in this case, the quadratic term where H of U star is going to be the Asian evaluated at U star. So gradient is the first order derivative, Asians are the second order derivative. So then if we make a reparameterization of our limit state function, as we just saw in module 7 when we were computing the sensitivity analysis. So we saw that by dividing this function by the norm of the gradient divided by the norm of the gradient, we could obtain that equivalent reparameterization of our limit state function, where we have now the norm of the gradient times beta minus alpha u. So we have here equivalent formulation as we had here. And in this case, plus 1 over 2, the norm of the gradient, simply the term we divided here, times exactly what we have here, the second order term. And where, as I said, h of u star is going to be the Asian of my limit state function, meaning the second order partial derivative. So it's the second derivative of g of u star divided by ui divided by uj for every pair of possible dimension. So here what we had is our problem in the center normal space. So with form, what we can see here in cyan, we were approximating our limit state function and also our limit state surface by a plane or a line. With SORM, we're going to approximate it by a polynomial of degree 2 terms of parabola. So what we're going to do is that we're going to have a first step as a rotation of referential in order to align everything with respect to a single dimension. So in this case, we're going to make sure that the vector alpha, alpha hat, sorry, is reoriented towards my last dimension. And again, this is only a convention that we use. So in this case, that alpha at, it can be arbitrarily oriented. I want to make sure it's oriented with respect to the last dimension. What is it going to be the effect of this rotation? Is that I'm going to remove the curvature with respect to the last dimension. So the curvature are going to be expressed with respect to all the dimension except the last one. So basically, the probability content with respect to the last dimension is going to be carried by beta, the distance from the origin to that u star, And with respect to all dimensions that are not the last one, we're going to be expressing the curvature with respect to all these dimensions. And this is going to be the key idea behind SORM. So how can we perform such a rotation going from the standard normal space that we typically have, or U space, to a new referential U prime? So we're going to do this by multiplying U by a rotation matrix P. And we can do the reverse transformation by saying that U prime space times P transpose, or P transpose U prime, will gonna bring me back to my standard normal space U. So to obtain that rotation matrix P, we're going to use the Gram-Schmidt algorithm. So that Gram-Schmidt algorithm will allow me to go from P times U equals U prime and to do the reverse rotation using the P transpose term. So P is that rotation matrix, where with the Gram-Schmidt algorithm, the specificity is that we want a rotation matrix such that the last row of that rotation matrix is my alpha hat vector. And that rotation matrix is such that P times P transpose is going to be equal to my identity matrix. So P is used as a rotation matrix, and we saw that P transpose bring me back to where I was, so P times P transpose is going to be the identity matrix. And if we do P times U star, the property is that's going to bring me in my design point for my last dimension. So what does it mean? P times U star is going to be 0 for everything except the last component, which is going to be equal to beta. For my gradient, I have something similar. If I do the gradient of the limit state function in the standard normal space, evaluated at, again, my design point, I multiply this by P transpose. I'm going to have 0 for all the component but the last one, which is going to be simply equal to the norm of the gradient, because I have reoriented everything with respect to simply the last dimension. So if we look at an example, the same example we saw in module 6 for form, I have this bar subject to a tensile force S as a resistance R, defined by the cross-section D of my bar multiplied by yield stress. D and S are independent. I have here the mean and standard deviation for each random variables. I have my two variable D and S, my mean vector, my standard deviation matrix. I have my limit state function R of x minus S, where R of x is D squared times f of y, where f of y here is simply deterministically known. I assume that both random variables are Gaussian for simplicity purpose here. So what we're going to have is that this is my original space. Okay, I have my x0 corresponding to mx. I use my IHL-RF algorithm to find my design point. I'm going to do this in the standard normal space, U here. Here, with the form analysis, I could have already found in module 6 what was my negative gradient, standardized gradient vector alpha hat, which is minus 0.88 and 0.47. This is that little blue vector. Then my rotation matrix P, we said that the last row of that transformation matrix is going to be alpha. And we can see here it's minus 0.488, 0.47. Perfect. I found this using the Gram-Schmidt algorithm, which enforced that this is going to be satisfied. Then it means that if I multiply every two coordinate vector representing a point in that U space, I do P times that two-dimensional vector, I'm going to obtain a point in my U prime space, where you see now that everything my vector alpha hat is reoriented with respect to the last dimension, and U prime star is going to be the design point with respect to the last dimension, and now the beta is the distance between the origin and that vertical point. So this is the goal. We reorient everything with respect to the last dimension, so that with respect to U2 prime, there's no curvature. Curvature are only expressed with respect to, in this case, a single dimension, U1. So I can decouple the distance from the origin and the parabola from the curvature of the parabola. So that greatly simplified the problem. So this is for a simple case where we have simply two dimensions. So in a general way, we can express our limited function by this second order Taylor series approximation, the same as we saw before. We remove the term, which is going to be the function evaluated at U star, because we knew it was 0. And by dividing by the ratio of the norm of the gradient divided by norm of the gradient, we could obtain this equivalent formulation. Okay, same trick we used in module 7. Now we're going to look at how can we go in the referential u prime and how can we find the curvature. So if we define the limit state function in the u prime domain, so u was our standard normal space, u prime is the one which has been rotated. So I can evaluate g of u by saying u is p transpose times u prime. So we saw that u prime was p times u. So u was p transpose times u prime. We can reverse that rotation by multiplying by p transpose. So p transpose times u prime is going to give me u. I can evaluate g of u. Divided by here, the norm of the gradient. So this is simply a scalar. So it's not going to change my limit state function. This is therefore mathematical simplicity because it's going to cancel out with another term where it's going to give you that formulation where this term here disappears. So it's going to give me this simpler formulation where I have beta minus alpha p transpose u prime. Okay, and alpha times p transpose u prime is going to give me here simply the rotation in the last direction. That's going to give me un prime. Okay, that's going to give me the dimension between the origin and the point with respect to only the last dimension. So p transpose times u prime is going to be u, and alpha times u is going to be the projection with respect to that last dimension. And then what we have here is we're going to have p times the Asian evaluated at my design points times p transpose. So since we do a rotation, we need to do the rotation on the second order term as well. So it's going to be p times Asian times p transpose. And if we regroup all these terms here in the matrix A, so we're going to divide this by that norm of the gradient as we saw here, we're going to have this matrix A that we can partition. So that partition is that on the last term, so last row and last column, I'm going to have a singleton representing only the terms for the last dimension, the one that has no curvature. The term A11 is the one we're going to be interested in, is going to be the curvature for all the matrices, all the dimension, but the last one. So in that case, the U1 prime associated with the A11 is all the U prime except the last one. So then what am I going to be able to say if I rewrite this by grouping all this P Asian times P transpose by A? What I'm going to do is that I'm going to rewrite these terms. Okay, I'm going to rewrite this quadratic term here by saying I'm going to split it into the A11 term. So it's going to be the U1 prime, so all the dimensions but the last one, times that matrix, which is going to be this one, so A11, so a matrix of all dimensions except the last one. We're going to have 2 times the A12 terms. So 2 times mu n prime minus beta times A12. So it's going to be n minus 1 by 1 matrix or vector times U1 prime plus ANN, my last terms, times UN prime, the last dimension minus beta square. And the particularity here is that since we're operating at point that is close to the design point, so un minus beta is going to be roughly equal to 0. So we can neglect those two contributions to the modelization of our parabola. So in that case, we're left with only these terms. So we're going to be beta minus un prime plus 1/2 of my vector u1 prime, a11 u1 prime. So this is going to be basically a parabola that is going to be centered, for which the apex is going to be centered at our design point u1 prime. So what do we have? 2 dimensions. There's some specific additional step we need to do. So for instance, our limited function in that rotated space u prime is going to be equal to beta minus un prime with respect to the last dimension plus 1/2 u1 prime transpose a11 u1 prime. So this is our parabola centered at u prime in the rotated space. But what we want is not this form. We want is this form where we have the same term that we have here. We have the same thing here. So the distance between the origin and the design point with respect to the last dimension only. So that's the distance from the origin of that parabola with respect to a single dimension, the last one, plus a term that involves here the curvature times each dimension with respect to prime prime. That indicates we're going to need to do a second transformation. Because in the terms we have here, what happened is that all the curvature might be intertwined with respect to all the remaining 1 to n minus 1 dimension. But we want to decouple these possible expression of curvature to obtain that simplified term where we have for each u prime dimension, u prime prime dimension, we want to have one curvature per dimension rather than having interaction between the curvature. So it's a bit like if I have a parabola like this, I don't want to have some interaction between my curvature, because remember, the first step was to say I have a, imagine this is my limit state surface in 3 dimension. I have some orientation, arbitrary orientation. I want to reorient this with respect to the last dimension. But you see that I can have interaction between my dimensions. So what I want is to reorient my limit state surface or my limit state function so that I can express my curvature with respect to single dimension. We're going to illustrate this in a moment. So we want to find that second transformation through the Q matrix here. We're just going to go from the U prime space to U prime prime space, a second transformation. And we can again do the reverse of that transformation by multiplying Q transpose by U prime prime is going to give me U prime. So that second transformation to go from the rotated or transform space to the one where all my dimensions are decoupled is going to be obtained by multiplying u prime primes times the q, that decoupling matrix, times my A11 matrix, q transpose u prime prime, where here q is going to be the eigenvalue decomposition. So in this case, I'm going to have in q the eigenvectors, and my kappa I, here my principal curvature, are simply going to be the eigenvalues. So q's are the eigenvectors, kappa I are going to be the eigenvalues of my A11 matrix. Okay. So as I said, kappa I are my eigenvalues of that decomposition. So the key here is first is for my matrix A11, how do I compute it? Okay, so remember it's a rotation matrix times the Asian. So first step is how do we compute the Asian? So Asians are second order partial derivative. So second order derivative of GU star evaluated with respect to pairs of UI, UJ. So I have two ways of expressing this. Is d of GU with respect to UJ, derivative of this with respect to UI, or vice versa with respect to the permutation of terms. In practice, we can evaluate this when we cannot do it analytically using numerical differentiation. So we have the difference between two gradient term divided by 2 times delta, the permutation we do, where these terms here can be explicitly represented by, if we look at this first left-hand term here, we're going to have the GU, which is permuted with respect to the ith dimension by a permutation, perturbation delta, with respect to the jth dimension delta. Then we're going to do the evaluation of that limit-taking function where we do a different permutation. So plus delta with respect to the ith dimension minus delta with uj divided by 2 times the permutation uj. We do the same thing here, but it's going to be minus with respect to the ith direction, plus with j, minus I minus j divided by 2 uj. And if we do this specific set of perturbation with respect to each dimension, we're going to approximate this second order derivative. So this is something that is trivially implemented in computer code. Then the second thing, once we have our Asian, is that we need to find our rotation matrix, because A11 is going to be P times Asian times P transpose. And that rotation matrix, where we're going to have the last row is going to be our vector alpha. So that little script will give us directly that P matrix, where you pass as entry the alpha vectors, which is going to return P, where the last row is alpha at. And this calls the Gram-Schmidt decomposition or the Gram-Schmidt algorithm, which is defined in this script on the right-hand side. Then to compute A is going to be P times Asian that we compute here, P transpose, divided by the norm of the gradient. Norm of the gradient we already obtained using a form analysis, as we've seen in module 6. And that's going to give us is n by n dimensional matrix. We're going to remove the last column. We're going to remove the last row. We're going to have our A11. And what we're going to do is simply going to do an eigenvalue decomposition of that A11 term. The eigen vectors are going to be our Q matrix, the second transformation. Eigenvalues are going to be our kappa I, our principal curvature. And in practice, we don't necessarily need that Q. We're only going to use the kappa I, the principal curvature, because once I have the beta from a form analysis and I have the kappa I, I can directly compute that probability of failure using a SORM analysis. So it's going to be CDF of minus beta. I already have this from a form analysis times a correction on a form analysis to take the product of 1 divided by the square root of 1 plus psi, the ratio of the PDF of beta divided by the standard normal CDF of minus beta, times kappa I, the curvature for each of my dimensions. And here are the dimensions. Remember, it's going to be the U prime prime space where everything is decoupled. So one of the limitations of that SORM method is that when we have g of x, the limited function that takes a large computational time, computing the Asian might become difficult because if we have a large number of dimension, the square of the number of terms as we have dimension in our Asian matrix. So this can become difficult. But there are multiple methods to be able to quickly approximate that Asian. One of them is published in the following article by the Karigian and Stefano, which use the algorithm similar to what is used to obtain the design point, the IHLRF algorithm, in order to approximate these second order derivatives. So if we look at an example, first in 2-dimension, the same example we saw previously and that was already solved in module 6.1 for SORM, we want to compute the probability of failure using SORM. So we're going to compute our Asian, we're going to compute our rotation matrix P, where the last row is going to be our vector alpha. So it gives me what I have here. I'm going to take my A11 term. So this is that 0.051. That's directly going to be my kappa 1. When I have only 2 dimensions, I don't need to do the second transformation because I already have it. It only applies for cases where I have more than 2 dimensions. So in this case, I can compute my SORM approximation of probability of failure by using that same approximation I added with form, so CDF of minus beta, and then I have the correction for my last curvature. So in this case, it's going to be the psi computed only for that kappa 1, where kappa 1 is going to be a curvature with respect to the first dimension. So you can see, just as we did before, original space, standard normal space, this is the space where we have our rotation. We computed with our kappa the curvature with respect to the first dimension. So with form, we had a probability of failure estimate at 0.1. With SORM 0.0966, Monte Carlo, using a very large number of sample, we have 0.967. So we can see that we're very close to the Monte Carlo solution, and we can see that we have a little closer approximation to reality, because instead of having a line, such as in the form approximation in cyan, in green we have that quadratic terms that reduce our approximation error. But here it's not representative of the full extent of the SORM method, because we have only 2 dimensions. So we don't need that second transformation to really be able to decouple our curvature. So now we're going to look to illustrate this at a 3-dimensional problem. So we have now a column subject to a compressive force P, a bending moment M, and that has a yield stress of Y. Okay, those 3 are represented by random variable, P and M by log normal, Y by gamma. We have some correlations. We're going to use a Natat distribution that we've covered in module 3 in order to model that joint distribution between those 3 variables. And now we're going to see need of our true transformation. So again, the same steps. First, we compute the Asian with respect to our limit state function with respect to each pair of variable. We're going to compute our rotation matrix P, where the last row is going to be the alpha hat vector, where we're going to build this matrix using the Gram-Schmidt decomposition or Gram-Schmidt algorithm. Then we compute our A matrix. So A is going to be P times Asian times P transpose, P being, again, our rotation matrix. And I'm going to discard the last column, last row. That's going to leave me with A11. A11 in this case is going to be a 2 by 2 because I reoriented everything with respect to the last dimension in the standard normal space. So now what I'm going to do, I'm going to compute the principal curvature by taking an eigenvalue decomposition of that 2 by 2 matrix. And once I have this, I'm going to correct my form approximation. This is only phi, capital Phi, so normal, standard normal CDF of minus beta by the curvature with respect to the first two dimensions. So if we look visually, how does it look like? We can see that with the form analysis, we obtain a probability of failure. This is estimated at 0.57. With SORM, we correct this to 0.70. And we see that with Monte Carlo, with a very large number of samples, we obtain 0.68. So we got closer from 0.68 by the SORM compared to the form. Okay, we could really reduce the approximation error. And if we look at this, these curves here, so you can see this is the original space. So what you can see as with the curve here is going to be my limit state function. So my limit state function, as you can see here, sorry, my limit state surface. So it's because my limit state function is in 4 dimension, I cannot visualize it. What I'm visualizing here is the limit state surface. So the g of x equal 0. So this is going to be my design point in the original space. I have 3 dimensions, so it's going to be the 3 dimension I was having. It's going to be, if we look here in terms of ordering, and P, M, and Y. So in this case, this is my original space. This is the point, my design point. Then to do all the calculation and to find a design point, I went in the standard normal space. This is that standard normal space we're seeing here. So that standard normal space, this is the origin 0, 0. And the point is my design point U star. And you can see a little blue or a little purple arrow is going to be my alpha hat vector, my negative normalized gradient vector that points towards the failure domain, which is located somewhere here. So you can see that everything is around. So what I want to do with my first transformation that is involved into SORM is to take that space and I want to reorient it with respect to the last dimension. So I'm going to try to do it manually here. It won't allow me to, maybe I can do it here. No, I cannot achieve it. But basically we want to take this vector here and make it vertical. And this is what I'm getting here. Okay, so this is the rotation of this space. So I don't change the shape of that limit state surface. I just reorient that vector so that it is vertical. It's going to look like this. So you can see here, I have a reorientation of my space. But now if you look to with respect to each variable, so I'm only going to look with respect to U2 prime, you see that the curvature is an interaction between U2 and U1, because if I reorient with respect to U1, the curvature is somehow with respect to an interaction between U1 and U2. It's not directly represented with respect to one or the other. So the second transformation we want to do is that reorientation of all my curvature with respect to a new referential, where I have curvature with respect to each dimension separately. Okay, so this is what my second eigenvalue decomposition is doing, is simply reorienting these curvature to align them with respect to principal axis. And this is what the eigenvalue decomposition of my A11 matrix is doing, is that second transformation. So the first transformation is simply a rotation. The second one is an eigenvalue decomposition. And this is what allow us to, with minimal effort, being able to reduce our approximation error by replacing the limit state function from a plane to a parabola. And keep in mind that using a form method will always involve doing a form method first, because we need to compute the beta and we need to compute the design point. We can look here with Monte Carlo. We generated, I think it's 10 million points to look at what is going to be the fraction that's going to fall in the failure domain. And so form, as we said earlier, would reduce the approximation error compared to form. So the limitation of SORM is that now our limit state function is approximated by a parabola instead of a plane. This is great, this is better. But still, if g of x is more complex than a quadratic function, we're still going to have a limitation with SORM. So we can, in this case, again, rely on Monte Carlo simulations. So just like for methods, when we have a large number of dimensions, the probability content located at U star is fairly diluted in the large exponentially growing volume of space. So in that case, we might have a limited accuracy for the SORM method, just like we had with SORM as the number of dimensions grow. Despite being said, for practical application, typically form and SORM perform really well for structural applications. So in summary, the SORM method works by computing the Asian of our limit state function, and we can do it analytically if available. We can do it with a numerical derivative to compute the curvature of our limit state function at the design point. Once we have this, we need to find our rotation matrix, which is going to have as last row our alpha hat vector. We compute our A matrix, which is the rotated Asian matrix, and we're going to take the terms which exclude the last row and last column, and then we're going to compute the eigenvalues of this A11 matrix, and these are going to be the curvature. And once we have the curvature, we can directly approximate this term here using that simplified expression, which involves the form expression. So this is already what we have obtained with our form estimator that we're going to correct with these kappa I, where the psi, I remind you, this is simply the ratio of the standard normal PDF of beta minus divided by the standard normal CDF of minus beta. So, and where that P matrix is that referential rotation. So that concludes what we wanted to see with those analytical estimation methods for our probability of failure. The next step we're going to see is how can we extend everything we've seen so far from module 1 to 8 for the estimation of the failure probability for a component? How can we extend it to estimate the failure probability for complete system?